Greetings and welcome to Unit 2, Lesson 1. This is Part 2, where we will discuss function notation, evaluating a function, and a little bit of domain as well. So, notation. It's important for you to understand that vocabulary word, that it's simply how we communicate mathematically on paper. Think about there's a certain way to do a bowling score. You have to notate if it's a spare or if it's a strike. You notate in your foreign language class. Certain languages require an umlaut or some type of accent mark. Sometimes you notate in English. A sentence might end in a period or an exclamation mark or in a question mark. So now you just need to think about notation as how we communicate mathematically. What's convenient about it is function notation allows you to name a function so you aren't confused about which function you're talking about. So let's take an example. If I have y equals 3x plus 2, there's one function. And y equals x squared plus 6x plus 7 is another function. But they're both equal to y, so I don't necessarily have a name for each without saying the whole thing. What function notation allows us to do is to substitute in for y f of x. And then since x squared plus 6x plus 7 was a separate function, I named the quadratic g of x. I could have used h of x, r of x, k of x. That letter is simply the name of the function. And when you look at f of x and g of x, you never do anything mathematically with those sides. And on the next slide, when we evaluate a function, that'll become a little bit more clear. When you say this out loud in class or to a teacher or to another mathematician, you read it as f of x equals 3x plus 2 or g of x equals x squared plus 6x plus 7. So how do we evaluate a function? I'm going to give you the function named f, which is negative x squared plus 3x plus 2. I'm going to have us evaluate f of 2 and then f of negative 2. So let's look at f of 2. F of x is equal to the opposite of x squared plus 3x plus 2. If I want you to find f of 2, all it is a substitution problem. If I said, find the output when you input 2, this is how we use function notation to show our work. So f of 2 equals negative 2 squared plus 3 times 2 plus 2. So I substituted in 2 for those x's. Now I want to be clear about something with the next step. The opposite of 2 squared, because that negative is on the outside of the 2, it does not get squared, so it yields negative 4. So please be careful when you note the difference between the opposite of 2 squared and then the quantity of negative 2 squared. The first is negative 4. This would yield a positive 4. Again, in the first case, the negative is not being squared. In the second case, the negative is being squared. So please be careful, because if you type it in your calculator wrong, the calculator only knows what the user puts in. Back to the problem, the opposite of 2 squared is negative 4. 3 times 2 is 6. The 2 remains a constant. And then after I take negative 4 plus 6 plus 2, that yields 4. So when you see the function notation f of 2 equals 4, this translates to 2, 4 on the graph. Now let's focus on inputting negative 2. Again, it is simply a substitution problem. I input negative 2 in for x. And so notice how I've got a couple of double negatives going on. I have f of negative 2 equals the opposite of negative 2 squared plus 3 times negative 2 plus 2. It's important to note that the negative 2 squared does yield a positive 4, but the negative on the outside keeps it negative 4. 3 times negative 2 is negative 6. Then I add 2, which yields a final answer of f of negative 2 equals negative 8. This means when I input negative 2, I output negative 8. So the coordinate negative 2, negative 8 is a point on the graph. We're still evaluating a function, but I gave you something a little bit different. Instead of giving you a numerical value as an input, I gave you an expression. So we're taking the expression x plus 2 and we're putting it into the function negative x squared plus 3x plus 2. What I want to show you, however, is that we don't do this problem any differently than when we did numerical values. So notice how when I had 2 and negative 2, I substituted those values in for x. I am going to do the same thing here. Where I saw an x, I substituted an x plus 2, plus 3 times x plus 2, plus 2. So hopefully you can see that this first process is not any different than what I did with a numerical input. Now the remainder of this is going to require some algebraic simplification. Please remember that x plus 2 squared means x plus 2 times x plus 2. When any time you're squaring a number, you multiply it by itself. Then I use the distributive property, 3 times x to yield 6x, and 3 times 2 to yield 6, and carried my constant down of plus 2. Next, I'm leaving the negative on the outside, but I am going to use the distributive property with x plus 2 times x plus 2. Some of you might refer to this as FOIL. I took the first, which is x times x. The outer is x times 2, which is 2x. The inner is also 2x, which yields a 4x. 2 times 2 is 4. Then I carried down the 6x and the 8. Next, I distributed that negative to x squared, 4x, and 4, yielding negative x squared minus 4x minus 4. Carried down my 6x plus 8. Then I combine like terms. There is nothing to combine with the negative x squared, but negative 4x and 6x can be combined to make 2x. And negative 4 plus 8 is equal to 4. So when you input x plus 2, it yields another expression as an output, negative x squared plus 2x plus 4. Now we're going to talk about piecewise defined functions. And the first time you see this, you might be flummoxed by the way these look. But I want you to think about how you put on an outfit. Maybe you are like me. I'm not exactly the world's gift to shopping. I can't go to 3 different stores, find 3 different items, and put them together. I'm the person that generally looks at the mannequin and says, I like it, and I buy everything on it. Or I look at the rack and notice that they have put all the shirts or the tops and the bottoms together and tend to kind of buy that way. But there are a lot of you that like to change it up and you like to mix and match. So the same thing can occur in math. And we call these piecewise defined functions. You can take a piece of a linear function and a piece of a quadratic, and it creates a brand new function. Sometimes the pieces will meet, and other times they don't. So let's take a look at some examples of piecewise defined functions, and then we will do an example of how to evaluate them. So in the next slide, I'm going to be graphing them by hand, and I want you to follow along. Ultimately, you need to be able to evaluate them at this point. Graphing them by hand will be what we practice throughout the year, but I think you need to see how we graph them in order to understand a piecewise defined function. And here is our first piecewise defined example. They're easy to spot because there is a bracket that is attached to the function. And the reason you have a bracket is, in this case, we have 2 pieces that make the piecewise defined function, but you can have 3, 4, obviously an infinite amount of pieces. So you'll notice, let's look at the top. You see x squared minus 1 followed by a comma. Then you see the inequality x is less than 2. The inequality isn't anything we're going to solve. The inequality describes the type of inputs we use for that piece. So we only use the x squared minus 1 piece when our inputs are less than 2. Then when we look at the bottom of the function and we see x plus 1, we only use that piece when our input values are greater than or equal to 2. So I think it's easiest to describe this by looking at a t-chart. I have picked some values, and I am going to pick 2 first. I know it's in the middle of the numbers that I have there, but I think that this will be helpful. If I input 2, by definition, it would go into the x plus 1 piece because it uses all of the input values that are greater than or equal to 2. So when I take 2 plus 1, I get 3. This means at 3, it's going to have a closed dot because that is where it's defined. However, you also have to put that boundary into the top function. It would get an open dot, but what you have to do is figure out, do the pieces meet or not meet? So notice, when I put 2 into the top function, even though there's no equal bar, I have 2 squared, which is 4, and 4 minus 1 is 3. So I technically get an open dot from inputting it into the top function, but then it becomes a closed dot when I input it into the bottom piece. Therefore, the pieces of this quadratic, the x squared minus 1, and the line x plus 1 both meet or intersect at 2, 3. So the closed dot is going to override the open dot. Next, I am just going to start putting in some input values. Let's look at the input value of -2. That is less than 2, so I need to use the top piece. So -2 squared is 4 minus 1, and that gives me 3. Let's input -1. Again, it's an input less than 2, so I use the top piece. -1 squared is 1, minus 1 is 0. When I input 0, same story. It's an input value less than 2, so I'm going to use the top piece. 0 squared minus 1 gives me a -1. When I input 1, still a value less than 2. Therefore, I use the top piece. 1 squared minus 1 is 0. Let's go to the other side of 2. Let's go input 3. 3 now is an input value that is greater than or equal to 2. So I use the bottom piece, and 3 plus 1 is 4. Last but not least, and again I could keep picking more, but I think you'll get the point. When I input 4, I have to decide, do I put it in the top piece or the bottom piece? It goes into the bottom piece because it is an input value greater than or equal to 2, and 4 plus 1 is 5. So now I'm going to plot these points, and forgive, I'm not on the smart board, I'm on my laptop, so this might not be the most steady. I'm going to plot the point -2, 3. I'm going to plot the point -1, 0. I'm going to plot the point 0, -1. I'm going to plot the point 1, 0, and there hopefully you can kind of see the quadratic stuff going on. I'm going to plot the point 2, 3, and that kind of completes the quadratic portion of it. Okay, so remember this goes on like this. I know I kind of missed there, but I think you'll get the drift. And then I'm going to start plotting 3, 4, and then 4, 5. So then this graph becomes linear on that side. So it's kind of a goofy looking graph, but piecewise are. You've got a piece of a quadratic and a piece of a line put together to make a new function. Here's another example of a piecewise defined function. We have g of x is equal to the top piece, which is 3x plus 2, and we use that for inputs that are greater than 1. And then we use x minus 4, that function, for inputs that are less than or equal to 1. So similarly, since 1 is the boundary, 1 is the area where I use, on either side of 1, I'm using a different function. Let's see what's happening. Technically speaking, when I input the number 1, I have to use the bottom function because that's where it's equal to 1. So 1 minus 4 is -3. Next, I have to still put it in the top. And when I put 1 into the top function, I get 3 times 1, which is 3, plus 2, which is 5. So it can't be a function because that is 2 outputs. But because the pieces, the top piece has an output of 5 and the bottom piece has an output of -3, this is a situation where the pieces do not meet. So my closed dot is going to go at -3 because that is from the bottom piece where it was defined, and I will place an open dot at 1, 5. And when I start to graph this, this might make more sense. So now to get the function again, I just input -2 is less than 1, so I'm going to use the bottom piece, and -2 minus 4 is -6. When I input -1, that is a value less than or equal to 1, so I use the bottom piece, and -1 minus 4 is a -5. 0 is also a value that is less than or equal to 1, so I use the bottom piece, and 0 minus 4 is a -4. Now on the other side of 1, when I input 2, I will now switch to the top function because it's a value greater than 1 as an input value. So 3 times 2 is 6, 6 plus 2 is 8. When I input 3, I get 9 plus 2, which is 11. And when I input 4, I get 12 plus 2, which is, yes, I get 14. All right, so let's go graphing. Okay, as I graph, I would go to -2, -6, -1, 5, 0, -4, and at 1, -3, I get a closed dot. So here is this part of the function. When I switch to the other side, however, 1, 5, 1, 2, 3, 4, 5 gets an open dot because this is where the other line picks up, but it can't equal that. But 1.00001 is going to work in that function, so that's why it requires an open dot. So you do have to put the boundary into both functions to figure out if they're meeting or not. And since this one is not meeting, I have to put an open dot into that top function. So then I would plot the point to 8, 3, 11, and 4, 14, and that would be the other portion. So this is a rough sketch of what that piecewise function looks like. So how do we evaluate piecewise functions? You do them the same way we did other functions. It's just when you evaluate them, you have to determine should it go in the top or the bottom piece. So for instance, let's look at f of 1. I have to go to the f function because that's the name, and I have to input 1. Because 1 is an input less than 2, I have to use the top piece. So 1 squared minus 1 yields 0. So f of 1 is 0. When I have to evaluate g of 1, now I have to look at the g function. So I notice that 1 would have to go into the bottom piece because 1 is an input that is less than or equal to 1. So 1 subtract 4 yields negative 3. When I want to find f of 2, I have to go to the f function. I would use the bottom piece because my input is 2, and I use the bottom piece whenever an input value is greater than, or in this case, equal to 2. So 2 plus 1 yields 3. G of 0, I have to go back to the g function. 0 is less than 1, so that means I continue to use the bottom piece. So 0 minus 4 gives me negative 4. And when I want to find f of 0, I have to go back to the f function. I notice that 0 is an input that is less than 2, so I have to use the top piece. So 0 squared minus 1 is negative 1. When you're doing a piecewise defined function, it is still a function. For each input, you should get one output. You just have to figure out what piece you should use. And our last topic in this video is the domain of a function. A domain can be described explicitly or it can be implied by the expression used to define the function. I am going to teach implied domain in class, but the explicit domain of a function are fairly easy. If you're given a set of ordered pairs, like I have 3, 6, negative 2, 7, 5, 5, negative 4, 3, 0, 4, you have a finite amount of points. The domain is simply the x values. I listed mine in numerical order, but the x values are negative 4, negative 2, 0, 3, and 5. And that would be my answer to that type of homework problem. If I was given the domain explicitly in a table of values, then your answers are right in front of you. It's the X column. And again, you just list those. So in this case, I listed them from least to greatest in numerical order. So we have negative 9, negative 6, and I should have that as a 2, not a 1. Pi, and 8. Next time we're in class, we will discuss finding the domain implicitly, in other words, from an algebraic perspective, and then we will discuss two applications. Enjoy!